In this video, we will discuss various ways of obtaining new functions from old functions. We will start from the operation of translations. So suppose C is a positive number and y equals to f of x has got its graph looking like this. Then to obtain the graph of y equals to f of x plus c or y equals to f of x minus c, all you need to do is to shift the graph of your original function upward or downward by c units. So if this is a positive sign, then you have got upward. If this is a negative sign, then you shift it downward. So in graph, it basically looks like this. So if this is y equals f of x, then this guy will be y equals to f of x plus c, and this guy will be y equals to f of x minus c. All right, so this is what you can obtain from shifting the graph of y equals f of x vertically. Now let's investigate what the horizontal shifting do for us. If we want to obtain the graph of y equals to f of x minus c, or y equals to f of x plus c. So now the plus and minus c is inside the parenthesis. Okay, if we want to obtain the graph of these two guys, all we need to do is to shift it either to the right or to the left by c units. Well, it's depending on the sign over here. So here the rule seems to be a little bit opposite. So if you are seeing a negative sign in here, this means you need to shift the graph to the right. So as you could see from here, so if you shift this guy to the right by c units, what you will get is y equals to f of x minus c. And if you're seeing a positive sign over here, this means you need to shift the graph to the left by c units. So this will be the graph of y equals to f of x plus c. Okay, so to summarize the rules in simple words, well, left means plus, right means minus, and up means plus, and down means minus. All right, so in summary, so this is basically the rule over here. Now, if you're careful enough, you might notice that it seems to be not very consistent, because when you make the graph get to going larger, well, you have to minus a c over here, but plus a c over here. So this seems to be an inconsistency, but indeed it's not. So notice that y equals to f of x plus c is indeed y minus c equals to f of x. And y equals to f of x minus c is indeed y plus c equals to f of x. So more generally, if you want to translate the curve capital F of x comma y equals to 0, if you want to translate this curve by the vector a comma b, well, the new curve will be f of x minus a comma y minus b, well, equals to 0. So indeed, if you want to make this guy larger, you should replace x by x minus c, or you should replace y by y minus c. Well, but then if you replace y by y minus c, then you move the minus c to the right. So these two ways are indeed consistent to each other. Okay, so please try to play around with this by yourself a few times to get more comfortable with this. And we will also provide some additional examples in this video. Right, so the next operation will be stretching. And now let's suppose c is a number that's strictly greater than 1. So then if we want to obtain the graph of y equals to c times f of x, or if we want to obtain the graph of y equals to 1 over c times f of x, then all we need to do is to stretch or shrink the graph of y equals f of x vertically by a factor of c. Well, because c is greater than 1, so if you want to obtain the y equals c times f of x, that means you need to do a stretching, so where this guy is greater than 1. On the other hand, if this guy is smaller than 1, then you should consider shrinking. So these guys are what you can obtain by vertically stretching or shrinking the graph. So for example, if y equals to cosine of x and c equals to 2, then y equals to 2 cosine of x is simply stretched vertically from the y equals to cosine of x by the factor of 2. So if you look at the vertical direction, you see the y coordinates of the blue curve is precisely 2 times the y coordinate of the purple curve. On the other hand, if you want to shrink the graph by a factor of 2, so what you get is y equals to 1/2 cosine of x. As you can see, the y coordinate on the green curve is precisely half of the y coordinates of the purple curve. Okay, so this is vertical stretching and shrinking. And how about horizontal stretching and shrinking? Well, if we want to obtain the graph of y equals to f of c times x, or f of x divided by c, so for the first one, we need to shrink the graph of y equals to f of x horizontally by a factor of c. And for the second one, you need to stretch it. So let's actually look at another example. So let's say y equals to cosine of x. And again, we can take c equals to 2. Well, to obtain the graph for cosine of 2x, you need to shrink it by a factor of 2. So as you can see, if you fix the y coordinate and look at the x coordinate of the corresponding points on the blue curve, you will see that it's precisely 1/2 of the x coordinates on the purple curve. And this applies to all this, all the intersections over here. All right, so if you want to make this guy larger, you need to do shrinking. But on the other hand, if you want to make this vector smaller, then you need to do stretching. So as you can see, this will be the curve graph for y equals to what cosine of 1/2 of x. Well, you see that y equals to cosine of 1/2 of x is precisely obtained from stretching this purple curve horizontally by a factor of 2. Okay, so this is just the stretching and shrinking. Now let's also discuss reflecting. So if we want to obtain the graph of y equals to minus f of x, so notice that the minus sign is outside f over here. So this is over here. If we want to obtain the graph of y equals to negative of f of x, that means you need to change each y coordinate by its negative. So effectively, this is reflecting the original graph about the x-axis. So that's the graph for y equals to negative f of x. On the other hand, if we want to get the graph of y equals to f of negative x, so notice that the negative sign is now inside the parenthesis. If this is the case, then you need to reflect the graph of y equals to f of x about the y-axis. So this is what you will obtain after doing that. All right, so this is just the reflection. Now let's look at some examples. So given the graph of y equals to root of x, as you can see from here, so you are asked to use the transformations to graph the following functions. Well, the first one is y equals to root of x minus 2. The second one is y equals to root of x minus 2. And the third one is negative root of x. The third one, pure root of x. And the last one, root of negative x. Okay, so how do we do that? So for the first one, you see a negative sign over here. And moreover, it's actually really outside of the square root. So what you're supposed to do is to shift it downward by 2 units. So this is what you will obtain. For the second guy, because you see a negative sign, well, that's associated with the x over here. So this is essentially f of x minus 2, where n minus 2 is inside the parenthesis. So this means you need to shift it to the right. So if you shift the original graph to the right by 2 units, you will get the graph for the second function. For the third function, you see a negative sign outside, and so this means you need to reflect it about the x-axis. So this is what you will obtain. For the fourth one, well, you need to rescale, or actually, like say, stretch the graph vertically by a factor of 2. So that's what you will obtain. So just stretch it out vertically by a factor of 2. For the last one, because now, well, your negative sign is kind of inside the parenthesis, so you are supposed to reflect it about the y-axis. So this is what you will get. All right, so this is the example 1. Now let's look at the example 2, and we wish to sketch the graph of the function f of x equals x squared plus 6x plus 10. And the simplest way to do this one is not going to be plotting the points that connect the parabola like that. The simplest way of doing this is, again, by shifting. And in order to figure out the shifting parameters, we are going to use completion of square. We perform the completion of square to this quadratic function, and well, this means I need to find a square based on x squared plus 6x. And then I need the coefficient of 9 over here, so I can rewrite the 10 as 9 plus 1, so that the first three guys will combine into the square of x plus 3, and then with the plus 1 remain outside. So this is the end of the completion of square. So once you have obtained this guy, so then it's pretty clear that the graph of your function is obtained by translating the graph of y equals to x squared first to the left by 3 units, because this is plus 3, and then after that you shift it upward by 1 unit. So that way you will obtain the graph for your function. So basically means you start from y equals to x squared, you shift it left by 3 and up by 1, and that way you will get the graph for this function over here. Okay, so this is example 2 with the polynomial function. Now let's look at the trig function example. So if we wish to sketch the graph of the following functions, well, the first one is y equals sine of 2x, and the second one is y equals to 1 minus sine of x. Well, for the first one, well, the graph is simply obtained from compressing the graph of y equals sine of x horizontally by a factor of 2. So you start from the y equals sine of x. If you do the compressing or shrinking, well, what you will get is something like this. So this will be the graph for sine of 2x. Now for part B, well, in order to obtain the graph for y equals to 1 minus sine of x, well, we should first reflect the graph of y equals to sine of x about the x-axis. Well, this way we will get the graph of y equals to negative sine of x. Then we shift it 1 unit upward to get y equals to 1 minus sine of x. So if you do the reflection, then the graph looks like this. Then you shift it upward by 1 unit. At the end of the day, you will obtain this graph. So this will be the graph for y equals to 1 minus sine of x. Now let's look at a more complicated example. We wish to sketch the graph of the function y equals to absolute value of x squared minus 1. All right, so well, before handling this complicated situation, let's first graph the parabola y equals to x squared minus 1. Well, this is pretty easy. All you need to do is to shift the parabola y equals to x squared downward by 1 unit. So this is what you will get. Okay, so now to handle the absolute value, keep in mind that if whatever inside the absolute value is positive, well, then absolute value of that guy is simply itself. So this means, well, on this part of the graph, because x squared minus 1 is positive, so absolute value of x squared minus 1 is simply going to be itself. So the graph of the absolute value function over this part will be the same as what you see over here. But on the other hand, since this graph has got a part lying below the x-axis, and indeed this happens when x is between minus 1 and 1. But notice what the absolute value does to this part. Well, the absolute value of x squared minus 1 will simply be negative of x squared minus 1 when x is between minus 1 and 1. So this means, well, to obtain the graph of this guy, all we need to do is to reflect this part of the graph about the x-axis. Well, then at the end of the day, we will get something like this. Well, this will be the graph for the function y equals to absolute value of x squared minus 1. So the method discussed here applies to the more general context. So in general, you might be asked to sketch the graph of y equals to absolute value of f of x. Well, you first sketch the graph of f of x, and you will figure out the parts above and below the x-axis. Then for the parts above the x-axis, you keep it invariant. But when for the parts below the x-axis, you simply reflect it about the x-axis. So that way you will get the graph for the absolute value of f of x in general. All right, so this is example 5. And we shall also investigate a few examples from the exponential functions. So if we wish to sketch the graph of the function y equals to 3 minus 2 to the x, what should we do? Well, we first reflect the graph of y equals to 2 to the x power about the x-axis. So that way we get y equals to minus 2 to the x. And we will shift it upward by 3 units to get the function, the graph of this guy. So we start from this guy over here. We first perform the reflection, and then we shift it upwards by 3 units, and this is what we are getting. Okay, you're also asked to determine its domain and range. Well, from this graph, it's pretty clear that, well, the domain is simply everywhere, and the range will be negative infinity to 3. So y equals to 3 is the upper bound for the function values over here. All right, so this is the example for the exponential function. And let's look at another such example. So starting from the graph of y equals to e to the x, we wish to graph the function y equals to 1/2 times e to the minus x minus 1. And also we need to state the domain and the range. Well, we start from y equals to e to the x. Well, the graph looks like this. So we will first handle this minus x over here. So in order to handle this minus x, well, we will just reflect it about the y-axis. So this way we will get y equals to e to the minus x. Then to accommodate this 1/2 over here, all we need to do is to shrink by a 1/2 factor. So this way, well, originally the function passes through the 0.01, and now it's supposed to pass through 0, 1/2. And well, this is actually after this is the graph you obtain after shrinking. And finally, to accommodate this -1, all you need to do is to shift it downward by 1 unit. All right, so this is what you are getting at. And this will be the graph of this function. Okay, so from the graph, it's also very clear that the domain is everywhere and the range will be -1 to infinity, and -1 is not achieved. Okay, so these are the examples of graph operations. And now let's consider the arithmetic operation. So this is another way of obtaining new functions from the old ones. So let f of x and g of x be 2 functions respectively with the domain a and b. So we can construct the following new functions. Well, the first one is the sum function. So f plus g of x, well, this is simply defined to be f of x plus g of x. And because in this expression, both f of x and g of x have to make sense, so this sum function is defined only on the intersection of a and b. So the next one will be the difference function. Well, f minus g is simply defined to be f of x minus g of x. And similarly, the domain is a intersect b. So how about the product function? Well, the product function is defined similarly. So the product of fg is defined to be sending x to f of x times g of x. And the domain is again going to a intersect b. Okay, but for the quotient function, situation will be slightly different. So the quotient f over g is a function sending x to the quotient of f of x over g of x. Well, in order to make sense of this guy, well, first x has to be sitting in the domain a plus a intersect b over here. But moreover, we need to make sure that g of x does not take 0. So that's why the domain for this guy will have got the additional requirement that g of x is non-zero. We will conclude this video by the discussion of composition functions. So this is also a very important way of constructing new functions. Let's go through the detailed definitions here. So given 2 functions f and g, so the composite function, well, denoted by a f circle g, so this is also called a composition of f and g. Well, the composite function is defined simply by the formula, sending x to f of g of x. If you imagine the related functions as machines, so what this composite function does is the following. So first you have got x as an input. You first put it into the machine of the function g, and it will give you an output g of x. Then you will put this g of x as the input for the machine f, and then what you will get is the output of f of g of x. All right, so then we will simply define our function to be f circle g to be accepting this x as the input and giving out f of g of x as the output. So this is just the machine interpretation of the composite function. So how about its domain? So let A and B respectively be the domain of f and g. So then the domain of f circle g, so this is going to be a collection of x in the domain of g, such that g of x can be accepted as the input of f. So this means g of x has to be sitting inside the domain of f. All right. So this way we get this compact expression that x has to be in the domain of g and g of x has to be in the domain of f. All right, so this is the domain for the composite function. So let's look into a very simple example. So let's say f of x equals to x squared and g of x equals to x minus 3. We wish to find the composition f circle g and g circle f. All right, how do we do that? Well, we just do it by the definition. Well, f circle g of x, well, by definition, this is going to be f of g of x. Now, because f sends x to x squared, so if you replace this x by g of x, what you will get is g of x squared. So f will send g of x to the square of g of x. And now you can plug in g of x being x minus 3. So what you will get is the square of x minus 3. On the other hand, g circle f, by definition, is g of f of x. Well, g sends x to x minus 3, so g sends f of x to f of x minus 3. And now you can plug in f of x being x squared, so what you get is x squared minus 3. Right, so from this example here, you should note that the f circle g in general is not the same as g circle f. So please be very careful when you're trying to carry out the computation. Please make sure you follow these rules and do not confuse f circle g with g circle f. Now let's look into some more complicated examples. If f of x equals to root of x and g of x equals to root of 2 minus x, so we need to find each of the following functions and their domains. Okay, let's focus on A first. So part A, we wish to find f circle g, which is defined to be f of g of x. Now, f of x sends x to root of x, so f of g of x would then be root of g of x. And now if you plug in g of x, you will get root of 2 minus x. Okay, so this is simply the same as 2 minus x to the 1/2 power and to take another 1/2 power. So by the product rule of the exponential function, you should realize that this is nothing but the 4th root of 2 minus x. So please make sure you're completely comfortable with this algebraic manipulation. All right, so this is the f circle g. Okay, so the domain for this guy is pretty simple. So 2 minus x has to be greater or equals to 0. But once you get the root of 2 minus x, so this guy is automatically greater or equals to 0. So there's nothing to worry. So all we need to make sure is that 2 minus x is greater or equals to 0. So the answer for the domain is simply the closed interval minus infinity to 2. Okay, so this is part A. Now let's look at part B. For g circle f, by definition, we're looking for g of f of x. Because g sends x to root of 2 minus x, so g sends f of x to root of 2 minus f of x. And now we can plug in f of x equals to root of x to get our conclusion that g f of x, so this is nothing but root of 2 minus root of x. All right, so to get the domain for this guy, notice that first, my x has to be sitting inside the domain of f. So this means this guy has to make sense, so x has to be greater or equals to 0. And moreover, we need to make sure that whatever inside here, namely 2 minus f of x or root of x, we need to make sure that this guy is also non-negative. So the requirements are simply x greater or equals to 0 and 2 minus root of x greater or equals to 0. Okay, solving this inequality, you will get x to be in the closed interval between 0 and 4, or well, by the interval notation, it's simply going to be closed interval 0 to 4. Right, so this is the domain for G circle F. Now for part C, we are looking for F circle F. Well, this by definition, this is simply f of x. Well, f sends x to root of x. So f sends f of x to root of f of x. And now f of x is going to be another square root over here. So by the same reasoning as here, you should notice that this is nothing but the fourth root of x. All right, so this concludes that f circle f sends x to the fourth root of x. So the domain for this guy is simpler because as long as your x is greater or equals to 0, root of x is also greater or equals to 0. So there is really no restriction imposed by the outer function over here. So the domain will simply be this guy, or in interval notation, that will be the closed interval 0 to infinity. Finally, for the last one, G circle G, by definition, is G of x. So since G sends x to 2 minus x, so G would then send gx to root of 2 minus g of x. And then you plug in g of x, so that way you get this expression. Well, the domain for this guy is slightly more complicated. So first, you need to make sure that this guy is greater or equals to 0, so as to make sure g is defined. But also, you also need to make sure that whatever inside this square root has to be greater or equals to 0. So these are the two requirements. 2 minus x has to be greater or equals to 0, and 2 minus root of 2 minus x has to be greater or equals to 0. So solving this inequality, you will get the solution, x sitting between minus 2 and positive 2, and then, well, the boundary points can be achieved. So in other words, we get the closed interval minus 2 to 2. Okay, so this concludes this example 7. Finally, let's look at the following two examples. So for the example 8, we wish to find f circle G circle H, where f is a fraction, x divided by x plus 1, g is the power function x to the 10th power, and h is the linear function x plus 3. Okay, so still by definition, f circle G circle H of x. So this is simply going to be f of g of h of x. Now, since f sends x to x divided by x plus 1, so we replace this x by g of h of x, this is what you will get. All right, so now for g of h of x, well, remember g sends x to x to the 10th power. So if you replace this x by h of x, this is what you will get. That will be h of x to the 10th power divided by h of x to the 10th power plus 1. And finally, you can plug in h of x equals x plus 3. So the result will be x plus 3 to the 10th power divided by x plus 3 to the 10th power plus 1. I think this is already a simplified form. There's no way to further simplify this expression, so it will be good to keep it like this. Okay, so for the last problem, given that capital F of x equals to cosine square of x plus 9, we wish to find functions f, g, and h such that capital F equals to f circle G circle H. Okay, so this example is extremely important when you are doing the chain rule to find the derivative of certain composite functions. Now let's actually do this. So the obvious way of finding such kind of three functions just work from outside to inside. So you see that the most outside function is actually going to be the square function. So the most simplest choice is going to be take f of x equals to x squared. And then the next layer, it will be the cosine function. So I will just do g of x equals to cosine of x. And finally, the innermost layer, that will be x plus 9. So I can just do h of x equals to x plus 9. All right. So yeah, if you're not very convinced, you can try to verify. So the f circle G circle H in this guy, and you compute it over here. So f sends x to x squared. So f sends g of h of x to be g of h of x squared. And then g of x equals to cosine of x. So g of h of x equals to cosine of hx. Finally, you can plug in h of x, and what you will get is cosine of x plus 9 squared. Well, this is precisely the square of this cosine of x plus 9 in the statement of capital F. All right, so just one last note. The solution is not unique. So for example, I can also take f of x equals x squared, but I will just perturb my choice of h and g. So I will just choose g of x to be cosine of x plus 1 and h of x equals to x plus 8. Well, you should be able to check that this equality still holds. All right, so when we are discussing chain rule, you are supposed to find such kind of f, g, and h without much thinking. Well, it's not very difficult, but just you need to get some exercise to get used to it. So I will provide some exercises for you to get used to such computations. Okay, so that concludes the video, and please attempt the homework exercises before coming to class.